Here we have our 4-bit divider circuit, which has two inputs, input A and input B, and it basically computes A divided by B to give two outputs. So the first output is going to be int A divided by B, which is the integer part. Then the second output is going to be modulus of A divided by B, which is the remainder part. Okay, so let me just go through some examples and sort of like demonstrate how the circuit works. So let's try maybe with simple examples. For example, right here, as you can see, I have my MSB, right? And then this is my LSB. So that means I'm going to be counting starting from here, going upwards, right? So this is actually 1, 1, 1, 0, which is 14. Then here we have 0, 0, 1, 0, which is 2. So 14 divided by 2 should give me 7, right? 7 remainder 0. So let me just run it. And as you can see, I have 0, 1, 1, 1, which is 7, remainder 0 in this case. Okay, so let me try another example. Um, so right here I have so right here I have 1, 0, 1, 0, which is 10 divided by 0, 0, 1, 1, which is 3, right? So 10 divided by 3 should give me 3 remainder 1. So let me run it. And as you can see, I have 0, 0, 1, 1, which is 3 remainder 0, 0, 0, 1, which is 1. Okay, yet another example. Um, okay, let's see. So this is 1, 0, 1, 1, which is 11, right? Divided by 0, 0, 1, 0, which is 2. 11 divided by 2 should give me 5 remainder 1. So let's run it. As you can see, I have 0. Right here, I have it's actually 0, 1, 0, 1, which is 5. Remainder 0, 0, 1, right? Which is basically 1. Now let me try maybe. Okay. Last two examples. Um, let's try maybe this one. Okay, so I have 0, 0, 1, 1, which is 3, divided by 0, 1, 1, 0, which is 6. So 3 divided by 6 should give me 0 remainder 3, right? So let me just run it. And as you can see, I have 0, 0, 0, which is 0, remainder 0, 0, 1, 1, which is 3. Okay, now this is the last example. Just stop this one. The last example I'm gonna have so last example I'm gonna have 15, 1, 1, 1, 1 divided by 0, 1, 0, 1, which is 15 divided by 5, which should give me 3 remainder 0, right? So let me just run it. Yeah, so right here I have 0, 0, 1, 1, which is 3, remainder 0. Okay, so yeah, that's basically how the circuit works. So I'm just going to go through each and every component and explain its purpose. So right here I have my full adder, which basically computes the sum of input B and the current value stored in the memory. And then the output is going to be stored back to the memory. So I actually have a loop going on here. And then I have my full adder, which is basically going to compute the sum of input A and the 2's complement of the value stored in the memory. In other words, it computes input A minus the value stored in the memory. Now let's talk about the comparator. So the comparator is basically going to check to see if the stopping condition has been met. So when that happens, it basically sends a signal which cuts off the clock, thus stopping the entire loop from running. Lastly, I'm just going to talk about the counter. So the counter is simply going to be keeping track of the number of times that I've added B to itself. Okay, so that's the whole logic of the circuit. So now I would say some obvious limitations are I can't really handle larger numbers. So for me to handle larger numbers, I would need to increase the number of bits, increase memory, increase the number of full adders that I'm using, even comparators and counters as well. But the obvious limitation right here is division by zero. As we all know that dividing a number by zero gives you an undefined result, right? So let me show you what happens if I try to divide a number by zero here. So as you can see, this is 15 divided by zero, right? And I'm running it. And as you can see, this circuit is going to keep on running indefinitely, right? So yeah, that's like the major limitation that it has. I mean, it makes sense, you know, even if you add like zero to itself infinite number of times, you still wouldn't be able to get to 15. So yeah, that's basically the whole circuit. So thank you guys for your time and peace out.